Today is the day. Our traditional podcast about fractals and other infinities is ready. So let's start right now.
uh, I want you to try something. If you're listening to this right now, whether you're out on a walk or sitting at your desk, commuting, whatever, just hold your hands up and look at them.
Really look at them.
Yeah, really look.
What if I told you that the jagged edge of the cloud floating outside your window right now isn't actually a three-dimensional object? Like, what if that cloud, with all its chaotic bumps and wisps, is actually a highly complex shadow being cast into our world by a perfectly smooth four-dimensional structure?
I mean, it sounds like pure science fiction, right? Or maybe some late night dorm room philosophical debate. But mathematically speaking, if you follow the geometry far enough down the rabbit hole, that proposition becomes, well, incredibly difficult to disprove. We're so conditioned to trust our eyes, to assume that the three dimensions we move through are the absolute limits of reality.
Right, and that assumption is exactly what we are dismantling today. Welcome to the deep dive. For those of you listening who love physics, cosmology, and the hidden math of reality, you really need to buckle up for this one.
Yeah, definitely.
Today's mission is to completely shatter your conventional understanding of fractals. We are pulling from an absolutely mind-bending set of research notes titled Fractal Studies number 28. And our goal today is to trace a line from the fundamental math of repeating shapes all the way to a literal cosmological model of the entire universe.
Which requires a massive shift in how we perceive the world. Usually when people hear the word fractal, they picture those hypnotic infinite zoom videos on the internet.
Oh yeah, the bright neon Mandelbrot sets.
Exactly. Or maybe they just think of a snowflake. They think of fractals as aesthetic curiosities, or psychedelic screensavers.
Right, like the classic dorm room poster aesthetic. But the research we're exploring today treats fractals completely differently. It argues that fractals are actually algebraic building blocks, like they are the structural DNA of reality. We are going to look at how mashing different fractals together creates emergent biological complexity, and how everything from the neurons firing in your brain right now to the cosmic web of dark matter tying galaxies together, how all of that shares the exact same underlying mathematical architecture.
To get there, though, we first have to unlearn how we've been taught to categorize these shapes. Traditionally, geometry has been a very comforting binary discipline. You draw a square, you measure its sides, and it sits finitely on the page. Even when mathematicians first started categorizing fractals, they tried to force them into neat, descriptive buckets based on, basically where they came from.
The classic descriptive is you have your geometric fractals, like the Cox snowflake, where you take a triangle, add smaller triangles to the middle of lines, and just repeat it forever.
Right.
Then you have algebraic fractals, which are generated by feeding numbers through a complex equation over and over. You have stochastic fractals, which use random processes to model things like the stock market or Brownian motion. And finally, you have natural fractals, the literal trees, lungs, and coastlines we see around us.
But those categories are a dead end. They are purely descriptive. It's like classifying animals based on whether they are fluffy or scaly. It tells you what they look like, but absolutely nothing about their underlying genetics, how they evolved, or how they interact. I mean, if I hand you a geometric fractal and a stochastic fractal, those traditional categories give you no mathematical tools to combine them.
Which is a huge problem if you're trying to figure out how the universe is actually built, because the universe isn't neatly segregated. It's a messy blend of determinism and randomness. So to really understand fractals as structural building blocks, we have to look at the mechanical engine underneath them. The research points to a mathematical foundation formalized back in the 1980s by a mathematician named John Hutchinson and later popularized by Michael Barnsley. It's called an iterated function system, or IFS.
This is where the math gets incredibly elegant. An iterated function system strips away the visual shape entirely. It says that a fractal isn't a picture at all. It is a set of instructions. Specifically, a finite set of what we call contraction mappings.
Let's visualize that, a contraction mapping.
Imagine a massive complex shape sitting on a table. Now imagine a mathematical rule that acts like a magical shrinking machine. It takes that shape, shrinks it down by a very specific ratio, say by exactly half, and then maybe rotates it a few degrees and translates it, meaning it slides it to a specific spot on the table. That entire process is one contraction mapping. An IFS is simply a collection of several of these shrinking and moving rules.
Okay, so I have a handful of these shrinking rules. If I apply them over and over, what actually happens?
The magic of an IFS is that if you apply these shrinking rules infinitely, regardless of what random blob of ink you started with, the system will eventually settle into one and only one final shape. This is called the attractor. And the attractor has a paradoxical property. The entire massive shape is perfectly mathematically equal to the union of its transformed selves.
I want to make sure you, the listener, really picture this because it's the key to everything that follows. Think of a fern leaf, a classic natural fractal. The whole leaf is made of smaller branches. Each smaller branch looks exactly like the whole leaf. An iterated function system says that the fern isn't defined by the green biological matter, it's defined purely by the geometric rules that tell the big leaf how to perfectly nest itself into the smaller branches. The shape is the rules.
Precisely. And once you accept that the shape is just a physical manifestation of these contraction rules, a whole new world opens up. Because if fractals are fundamentally just sets of mathematical instructions, then we can do algebra with them. We don't have to just look at them, we can operate on them.
We can add them, we can multiply them.
We can compose them. The research highlights a specific operation called alternating composition. So imagine you want to combine fractal A and fractal B. You don't just glue them together side by side, you weave their mathematical DNA.
So fractal A has its own specific shrinking rules, and fractal B has a completely different set of shrinking rules.
You alternate them. You take an initial space, apply all the shrinking and moving rules of fractal A. Then you take that new result and you force it through all the shrinking and moving rules of fractal B. Then A again, then B again, out to infinity. You're forcing two completely different geometric realities to iterate on top of each other.
Okay, my brain is trying to visualize the result, and it feels like a geometric car crash. What does that even look like? More importantly, how do you measure it? Because fractals are defined by their fractional dimensions. That's where the name comes from. They aren't 1D lines, and they aren't 2D squares. They sit somewhere in between, like 1.5D. So what happens to the dimension when you weave two different fractals together?
It creates a new hybrid dimension, and the researchers provide a beautifully concrete formula for calculating this composite dimension. Without getting too bogged down in the raw algebra, the way it works is essentially a weighted average.
A weighted average of dimensions. Let's explore that mechanism for the math fans. How does the math weight them?
So it looks at the original dimension of fractal A and the original dimension of fractal B. But it doesn't just split the difference. It weights each dimension based on how aggressively its parent fractal shrinks space. If fractal A's rules shrink space very rapidly, meaning its contraction ratio is tiny, it exerts a different gravitational pull on the final dimension than fractal B. You calculate the natural logarithm of those shrinking factors to find out how dominant each shape's spatial footprint is, and blend them accordingly.
Wait, let me unpack this. You're saying the composite dimension alpha comp is literally a fraction where you multiply the dimension of each fractal by the natural log of its contraction ratio and divide by the sum of those natural logs.
Yes, exactly. The formula is alpha comp equals the sum of alpha I times the natural log of rho I, all divided by the sum of the natural logs of rho I.
Wow, it's like mixing paint. But instead of blending colors, we are blending the fundamental fabric of space. If I have a red paint that is incredibly thick and opaque, and a blue paint that is very watery and translucent, mixing a gallon of each doesn't give me a perfect 50-50 purple. The thick red dominates. In this math, the fractal that compresses space the most aggressively heavily influences the final dimension of the new hybrid object.
That's a fantastic way to look at it. And an interesting mathematical quirk of this alternating composition is that it is commutative. Just like mixing that paint, it doesn't matter if you pour the red in first or the blue in first. Fractal A composed with fractal B yields the exact same underlying dimensional structure as fractal B composed with A.
But wait, if we're just averaging these dimensions together, even with weighted scales, doesn't that just smooth everything out? Like, if I mix a super jagged shape with a slightly jagged shape, wouldn't I just get a medium jagged shape? The sources we're looking at suggest the opposite. They say that combining fractals creates explosive runaway complexity.
It does. And that brings us to the threshold of multifractal analysis. When you alternate these generators, you don't get a uniform, boring middle ground. The resulting geometry becomes so tangled and convoluted that a single overarching dimension is no longer capable of describing it.
Because different regions of the new shape are interacting in different ways.
Exactly. Imagine a vast mountain range. If you try to describe it with a single dimension, you are basically just calculating the average roughness of the entire continent.
Ruh.
But that average is useless if you want to understand the actual landscape. A multifractal approach throws out the single dimension and replaces it with what is called a spectrum of singularities. It maps out the distribution. It tells you 10% of this shape is as smooth as glass, 50% is as jagged as a rocky cliff, 5% is infinitely dense.
The research notes use a very specific mathematical tool to bridge the gap, called the Legendre transform. It relates to the Holder spectrum. Let's translate this for the listeners who might be trying to picture how we actually measure roughness mathematically.
Right, so the Holder exponent is a way to zoom in on one microscopic, infinitesimally small point on a fractal and measure exactly how rough it is right there. Not the whole shape, just that one specific pixel of reality.
So if I'm running my hand over a smooth wooden table, the Holder exponent is measuring a very smooth local texture. But if my hand hits a splinter, the Holder exponent at that specific coordinate violently spikes.
Yes. Now, the Legendre transform is a mechanism that takes a macroscopic global view of the fractal scaling behavior and mathematically unpacks it into a massive histogram of all those microscopic Holder exponents. It gives you the full spectrum of roughness.
The actual formula in the notes is something like f of alpha equals the infimum over q of q times alpha minus tau of q.
Yeah, that's it. Where Q is the moment order that acts like a microscope focusing on different levels of density. Alpha is the Holder exponent we just talked about. And tau of Q is the mass scaling exponent. It basically turns thermodynamics into geometry.
Which sets up an incredible computational experiment from the research. To test this theory, they actually built a Python framework. They took classic, well-understood fractals, the Cantor set, the Koch curve, and forced them together using these compositional algebras. They wanted to see what happened to that spectrum of roughness. And the result is staggering. When they combine the fractals, the Holder spectrum, the total range of available textures and dimensions expanded by 20 to 40%.
Let's throw in the implications of that 20 to 40% expansion. It proves that combining fractals does not just mix their traits. It generates entirely novel scales of self-similarity that did not exist in the parent shapes. The interaction itself breeds new geometry. You are creating textures and pockets of dimensional space out of thin air simply by forcing two rule sets to collide.
It's pure structural emergence. You aren't just getting a hybrid, you are getting something that transcends its origins.
And this isn't just an abstract curiosity sitting in a Python script. This exact mathematical emergence is what biology relies on to function. The most profound application of this in the text is the structural modeling of fractal dendrites in the human brain.
Let's look at the brain, because this is where the math physically manifests inside the listener's head. Neurons need to process information, and to do that, they have to reach out and connect to as many other neurons as possible, so they grow these branching structures called dendrites.
But nature operates under ruthless physical constraints. The brain has a rigidly limited volume inside the skull. Furthermore, building biological matter costs metabolic energy, specifically ATP, so the neuron is faced with an optimization problem. How do I maximize my surface area to make billions of synaptic connections while minimizing the sheer volume of biological material I have to grow and keep alive?
And the answer is to use a composite fractal geometry. The researchers modeled this, looking for the absolute mathematical optimum. They found that for a neural network to be as efficient as possible, a neuron should have a branching factor between 2 and 3, meaning each biological wire splits into 2 or 3 smaller wires, and it should only do this to a depth of 3 to 5 levels.
If it branched to 10 levels, the microscopic wires would be so incredibly dense that there would be no room for blood vessels, glia, or the metabolic machinery needed to power them. The neuron would literally starve itself.
And if it didn't branch enough, you'd just have a thick, straight wire. Very easy to keep alive, but terrible for processing complex thoughts because it barely connects to anything. So nature found the exact middle ground. The research defines the optimal fractal dimension of this biological structure, and the number is astonishingly specific. D is approximately 1.58.
1.58. It is the biological sweet spot of the universe.
Let's visualize what a dimension of 1.58 actually means.
Well, a dimension of 1 is a straight line. Minimal energy, zero complex connectivity. A dimension of 2 is a solid sheet of paper. Maximum local connectivity, but computationally explosive and physically impossible to layer infinitely within a sphere. 1.58 sits right in the golden zone. It is sparse enough to allow the physical infrastructure of the brain to breathe, but dense enough to allow for massively parallel, multi-level pattern recognition.
The research makes a fascinating point about that pattern recognition. It says that this specific 1.58 dimensional composite structure prevents a combinatorial explosion. If your brain tried to wire every single thought linearly, connecting A to B to C, the number of wires required would exceed the number of atoms in the universe. But by using this multifractal structure where the connections themselves are organized in overlapping self-similar scales, the brain can process incredibly complex concepts simultaneously without short-circuiting.
Your thoughts, your memories, your ability to understand this very conversation is physically predicated on the algebraic composition of fractals, resulting in a 1.58 dimensional biological network.
Which is awe-inspiring. But it also forces us to confront a terrifyingly deep question. If the abstract mathematical formula on a chalkboard and the wet biological neurons in our skulls are both converging on the exact same fractal geometry, what is a fractal, fundamentally? Why does this geometry exist at all?
This is the pivot point where the research moves from advanced algebra into what we might call mathematical metaphysics. It introduces the projection hypothesis, and it is, without a doubt, the most radical concept in the entire study.
The hypothesis suggests that the fractals we see, whether it's the Mandelbrot set rendered on a 2D computer monitor or the 3D branching of an oak tree in the forest, are not the actual objects. They are projections. They are shadows.
The math suggests that the true dynamics generating these shapes are happening in significantly higher dimensional spaces. We are merely observing the lower dimensional footprint of those dynamics.
Let's break down the mechanics of how a shadow is cast in math. The text uses an operator formula where f of x is the fractal we see. And this visible shape is the result of a projection operator shining light on a dynamic, evolving system in an n-dimensional space. To ground this, let's use the most famous fractal of all, the Mandelbrot set.
Everyone can picture the Mandelbrot set. It looks like a bizarre, infinitely fuzzy bug surrounded by swirling psychedelic patterns. We perceive it as a two-dimensional image because it is graphed on a 2D plane. It has an x-axis and a y-axis, the real and imaginary numbers of the complex plane.
But the research tells us to look at the engine generating that image. The formula for the Mandelbrot set isn't static, it's iterative. Z next equals z current squared plus a constant. You take a point, feed it into the equation, get a new point, and feed that back in. You do it thousands of times.
And that iterative process means you are introducing a third dimension, which is time. The Mandelbrot set is not a photograph. It is a dynamical process unfolding over a temporal axis. The image we see is just a map of which points eventually explode to infinity over time and which points stay trapped.
Okay, so it's a 3D process projected onto a 2D screen. But the research pushes it even further. It argues the Mandelbrot system actually lives in a 4-dimensional phase space. Let's explain what a phase space is for the listener because it's crucial for understanding this shadow concept.
So in physics, a regular space just tells you where something is, its coordinates. A phase space tells you where something is and exactly what it is doing at that moment. So you don't just plot the x and y coordinates of the Mandelbrot point. Because it is a chaotic system governed by extreme sensitivity to initial conditions, you also have to plot the rate of change of x and the rate of change of y.
So position x, position y, velocity of x, and velocity of y. 4 variables, 4 dimensions.
Precisely. The intricate, infinitely complex boundary of the Mandelbrot set, that iconic fuzzy edge where all the chaotic beauty lives, is mathematically equivalent to a strange attractor inside a 4-dimensional dynamical system. When you look at a poster of the Mandelbrot set, you are literally looking at a 2-dimensional cross-section of a 4-dimensional chaotic phase transition.
Let's go back to my coffee cup analogy from earlier because I think it perfectly captures the mechanism here. Imagine I am holding a perfectly smooth white ceramic coffee cup. It's a simple, elegant 3-dimensional shape. But imagine I am standing in a pitch black room and I hold the cup in front of a violently flickering strobe light and it casts a shadow on a deeply textured rocky cave wall.
The shadow that hits the wall is going to look incredibly jagged, distorted, and wildly complex.
Exactly. If you were a 2-dimensional being who lived on that cave wall and you spent your whole life studying that shadow, you would calculate its fractal dimension, you would map its chaotic boundaries, and you would conclude that the object creating it must be unimaginably rough and mathematically torturous. But you'd be wrong. The object is a perfectly smooth cup. The apparent roughness is an illusion created by projecting a higher dimensional object into a lower dimensional space.
And the research states this explicitly. The fractal dimension is literally the trace of lost dimensions. The complexity we see is just the mathematical debris left over when higher dimensions are compressed down into our reality. They actually provide a generalized formula for this. The hidden dimension of the true system equals the dimension we observe it in, plus the fractal dimension that we measure.
D hidden equals D embedded plus D dynamic. That is amazing. The jaggedness is the math's way of trying to encode the missing dimensions. You see this powerfully in stochastic fractals, like fractional Brownian motion. These are formulas used to model seemingly random jagged paths, like how a speck of dust dances in a sunbeam, or how stock prices fluctuate.
But the research notes that fractional Brownian motion contains a specific parameter known as the Hurst exponent, which dictates memory.
Memory in a math equation, what does that mean mechanically?
It means the system's next step isn't just a coin flip. What it does next is deeply correlated with what it did 100 steps ago. The path is mathematically tethered to its own history.
Which proves the projection hypothesis. If the line looks completely random and jagged in 2D, but we can prove mathematically that it is remembering its past, then it's not random at all. The jaggedness is just the physical shadow of that hidden temporal memory. We are seeing a high-dimensional correlation crushed down into a 2D squiggly line.
It forces a complete paradigm shift. If the shapes we observe are just shadows, we can no longer classify fractals based on what they look like. We have to classify them based on the hidden machinery casting the shadow.
Which brings us to the next breakthrough in the research, section 4, the DNA of complexity. To map this hidden machinery, the researchers developed the concept of the generator. If the fractal is the shadow, the generator is the object casting it. And every generator, everywhere in the universe, can be defined by 5 strict foundational parameters.
These 5 parameters are the universal genetic code for complexity. The first is the state dimension. This is simply the number of independent variables needed to define the system state at any given moment. A simple pendulum has a low state dimension, right? But hurricane has a massive one.
Second is the parameter dimension. This is the volume of the rule book. How many constants, forces, or external pressures are acting upon the system?
Third is nonlinearity. This measures the intensity of feedback loops within the system. Is the output fed back in and squared, multiplying the effects of tiny changes, or is the relationship mostly linear and predictable?
Fourth is stochasticity. How much pure, unfiltered randomness is injected into the machine?
And finally, fifth, memory. We just touched on this. How deeply does the system consult its own historical states to calculate its future state?
5 numbers: state, parameter, nonlinearity, stochasticity, memory. With these 5 dials, you can describe the geometric engine of anything in existence. But the researchers didn't stop at defining them. They created a formula to calculate the overall power of any given generator. They wanted a single metric to compare the complexity of a snowflake to the complexity of a thunderstorm.
The math here is carefully balanced to reflect how these parameters interact. The power score isn't just simple addition. Memory, for instance, is scaled logarithmically because deep historical correlation compounds its structural influence over time. Randomness is multiplied by the state dimension because injecting noise into a massive multivariable system creates exponentially more complexity than injecting noise into a simple one.
Let's run some examples through this power equation because seeing the scores really anchors the theory. The formula is basically P of G equals ds plus dp plus n plus s times ds plus the log base 2 of m plus 1.
Exactly. So if we look at the pure geometric fractals from earlier, the Koch snowflake or the Sierpinski triangle, their generators are incredibly basic. Low state dimensions, mild nonlinearity, 0 randomness, and 0 memory. You crunch the numbers, their generative power is a very low 2.
Which makes intuitive sense. I mean, they're perfectly predictable. You could draw one perfectly with a pencil and a ruler if you had enough time. What about our 4-dimensional shadow, the Mandelbrot set?
The Mandelbrot generator operates in a dynamic complex plane. It has high nonlinearity because of that squared feedback loop, but it is entirely deterministic, right? There's 0 stochastic randomness. Its power score calculates out to 7.
So, a massive leap in underlying complexity from a simple triangle. But what happens when we look at generators in the physical world? Natural fractals.
Natural fractals sit much higher on the scale. The generator that creates coastlines, driven by erosion, geology, and fluid dynamics, has a power of 9.1. Romanesco broccoli, the plant that grows those mesmerizing perfect helical cones, has a power of 6.9. These systems are powerful because they blend rigid deterministic rules with environmental randomness.
And at the absolute top of the scale,
Fractal Brownian motion. Because its generator relies on infinite dimensional stochasticity, meaning it incorporates pure, unbounded randomness over continuous time. Its mathematical power approaches infinity. It's a fundamentally open system.
So we have a spectrum of generative power from 2 to infinity. The researchers then took all these scores, all these parameters, and plotted them on a 3-dimensional map.
This 3D map is arguably the first true evolutionary tree of mathematics. Imagine a spatial graph. The x-axis represents the state dimension. The y-axis represents the parameter dimension, and the z-axis represents the intensity of the nonlinearity and randomness. Every mathematical formula and natural pattern is a single dot floating in this space.
And when they populated this map, profound structures emerged. The dots clumped together into distinct families.
Yes. For example, the Mandelbrot set and the Julia set. Visually, they share almost no similarities. The Mandelbrot is that cohesive, bug-like shape. Julia sets look like scattered stardust or isolated swirling galaxies. But on this map of generators, they plot to the exact same cluster. The map proves they share the identical underlying mathematical DNA. They are generated by the exact same engine, just tuned slightly differently.
But when you plot natural fractals, the trees, the coastlines, the lungs, they map to an entirely different quadrant of the graph. The research proves mathematically that the fractal branching of a tree is not just a messy version of a mathematical equation. It is a distinct evolutionary branch of geometry, driven by a different balance of stochasticity and memory.
It perfectly isolates the mechanism of natural emergence, but it also raises an immediate glaring problem.
Right. We've defined the generators that make the shapes. We know the 5 parameters, but in the physical universe, things change. Evolution happens. So what is changing the dials on the generators? If a generator creates a fractal, what creates the generator?
We have to ascend to the meta level. The research introduces an operator called GG, the generator of generators.
Okay, a generator of generators. I'm going to push back here because this sounds like mathematicians just inventing layers of abstraction because they can. A rule for the rules. What does this actually mean?
It can sound overly abstract, I agree, but it is actually the only way to mathematically model a living universe. Think of biological evolution. A strand of DNA is a generator. It contains the parameters that dictate how a physical body is constructed. But the DNA itself is subjected to the environment, to radiation, to natural selection. The environment is the generator of generators. It operates on a slower time scale, applying meta rules to mutate and shift the parameters of the DNA itself over millions of years.
Okay, so the GG is the mathematical equivalent of environmental evolution. It maps a set of existing generators into a new, evolved set of generators.
Precisely. And just like the base generators, these meta-generators have their own power scores based on their own meta-parameters. The research calculates that a GG tasked with spawning Mandelbrot-like chaotic generators possesses a power score of 10.5. That's substantially higher than the base generator itself.
Because it holds the potential energy of the entire system's future evolution.
Yes. And this creates what the research calls the ultimate hierarchy, the causal chain of reality. The GG evolves the G. The G projects the fractal. The fractal is what we observe. If the GG possesses a high level of metastochasticity, meaning the rules of the universe are themselves allowed to mutate dynamically, it can spawn infinitely complex, naturally adapting structures.
We have literally scaled up from how to draw a triangle inside a triangle to the evolutionary algorithm of reality. And this leads us to the grand finale of the research, section 6, the cosmological fractal. Because if this hierarchical math, these generators and meta-generators, governs how neurons wire themselves and how coastlines erode, couldn't it govern the macrostructure of the universe itself?
For the astrophysicists and cosmology fans listening, this is where the research attempts a grand unification. They take this entire framework of multifractal algebras and generator parameters, and they apply it to the largest observable system in existence. They propose a multi-level fractal hierarchy of the universe.
They break reality down into 6 nested levels of geometry, starting at the absolute top, the cosmos, then scaling down to the galactic level, down to the stellar level, down to planetary systems, down to biology and life, and finally, down to the micro level of atoms and quantum states.
But they don't just offer this as a poetic metaphor. They derive a physical master equation of reality to model how geometry cascades down these levels.
Let's look at the master equation. It is an iterative formula that describes how the physical structure of level I generates the physical structure of level I plus 1. The equation is f sub I plus 1 equals ds times fi plus n times fi squared plus s times ri plus m times f sub I minus 1.
Let's translate those terms mechanically because they perfectly mirror the physical forces of astrophysics.
Let's do it. The first term is linear, state dimension multiplied by the previous structure. What is this doing physically?
This is the base self-similarity. This is the underlying dimensional scaffolding of spacetime. It represents the persistent geometric rules that apply whether you're looking at the spin of a galaxy or the spin of a hurricane. It ensures the universe is fundamentally cohesive.
Next term is nonlinear. Nonlinearity n multiplied by the previous structure squared. A squared feedback loop.
In astrophysics, this is the engine of structure formation. It represents gravity and thermodynamics. In the early universe, gas clouds were mostly uniform, but slight density variations, acting nonlinearly through gravity, began to violently pull matter together. The square term models how matter clumps, collapses, and branches out into distinct spiral arms and star clusters.
Then we have the stochastic term, randomness S multiplied by a noise function Ri.
This injects chaotic distribution of matter. It originates from the microscopic quantum fluctuations present seconds after the Big Bang, which were then magnified to cosmic scales by cosmic inflation. This mathematical term ensures that while galaxies share structural similarities, no two spiral galaxies in the universe will ever be exactly identical.
And then the final term, the memory term. Memory M multiplied by F sub I minus 1. This means the structure being generated is heavily influenced by the macrostructure of the level above it.
And this is where the research makes a staggering observation. As you move down the hierarchy of the universe, from cosmos to atoms, the fundamental state dimension drops precipitously. The state dimension of the cosmos is 10. Galaxies are lower, stars are 5, biology is 2, the microworld is 1.
The spatial freedom of the universe compresses as things get smaller, but what about the memory?
The memory parameter at the highest macro level of the cosmos is remarkably high. It's 0.45. This means the universe possesses a massive structural memory between its largest scales.
If the universe has structural memory, what does that shadow look like when projected into 3D space?
It looks exactly like the cosmic web.
The vast interconnecting filaments of dark matter and galactic superclusters that span the observable universe. When we map the universe, it doesn't look like a uniform soup of stars. It looks like a glowing, fibrous nervous system. It literally looks like a brain.
Exactly. The master equation demonstrates that the cosmic web isn't just an accident of gravitational drift. It is a mathematical inevitability. Because the cosmic generator has a high memory parameter, matter is geometrically forced to align along vast correlated historical filaments. The universe remembers its scaffolding, and galaxies form along the lines of that memory.
And the researchers point out that this master equation is essentially a control panel for reality. By tweaking the stochasticity or the memory, physicists can run simulations of alternate universes. If you run the equation with zero memory, the universe fails to form the cosmic web. You just get a boring, disconnected dust cloud of random stars. By tuning the dials of the generator, we are reverse engineering the Big Bang.
It provides a unified algebraic language for reality. From the way an atom vibrates, to the way a tree branches, to the way dark matter halos collapse, it is all governed by the alternating composition of these fundamental generator parameters.
What an absolute marathon of a deep dive this has been. We have covered a staggering amount of ground. We started by throwing out our basic understanding of geometry, replacing it with the iterated function systems that prove fractals are just instructions for contraction.
We explored how weaving those instructions together expands the multifractal spectrum, generating emergent complexities that biology utilizes to build the incredibly efficient 1.58 dimensional neural networks inside our own brains.
We confronted the projection hypothesis, the mind-bending realization that the jagged, chaotic fractals we observe are merely lower dimensional shadows of smooth temporal phase spaces operating in higher dimensions.
We mapped the genetic code of those higher dimensions using the 5 parameters of the generator, proving that nature and math follow distinct evolutionary paths. We scaled up through the generator of generators all the way to the cosmic equation.
It is a profound, unifying theory of everything. But before we sign off, I promised you, the listener, a final provocative thought. Something to keep you awake tonight. It comes from the very end of the research notes, and it builds entirely on this idea of the projection hypothesis and the universal generator DNA.
It is a concept that bridges astrophysics with astrobiology.
The researchers proposed this. If we now possess the mathematical formula to calculate the exact natural parameters of a generator, if we know what natural stochasticity and natural memory look like in a fractal, we could theoretically scan the universe for mathematical anomalies. We could look at the light curves of a distant exoplanet, or the structure of a radio burst, or the distribution of matter in a localized cosmic web, and run it through the multifractal algebra.
And if the numbers don't align with the natural generator map,
then you aren't looking at a natural process. You're looking at an unnatural fractal, a technosignature. We could find alien life not by listening for radio signals, but by looking for highly engineered, unnatural fractal geometries woven into the fabric of space or energy itself. Alien math, projecting a shadow into our telescopes.
A structural beacon of intelligence.
But the research takes one final dizzying step beyond even that. If the entire universe is a top-down hierarchical fractal, and if incredibly complex memory-driven fractals are just lower dimensional shadows of 4D or 5D dynamics, then what is human consciousness?
Well, the neural network processing that question right now is a 1.58 dimensional fractal.
Exactly. The researchers suggest that human consciousness might not simply be a biological byproduct wet tissue in a skull. The sheer density of our thought, our memory, our abstract reasoning, it might just be the three-dimensional projection of a much higher dimensional dynamical space. Your mind, your self-awareness, might literally be a four-dimensional process casting a shadow into the biological hardware of your brain.
It suggests that we are intricately, mathematically braided into the higher dimensional architecture of the cosmos itself.
Just a little something for you to mull over. The next time you step outside, look up and see the chaotic, jagged edge of a cloud floating in the sky. Remember, you aren't just looking at water vapor. You are looking at the shadow of higher dimensions.
I want you to close your eyes for a second, assuming you're not driving, of course.
Yeah, please keep your eyes on the road if you are.
Right, absolutely. But if you can, just imagine you're holding an object right in the palm of your hand.
Okay.
It's relatively small, like maybe the size of a baseball. And it has